Okay, so I'll be going over on 6B from the midterm. So 6 is about KD trees, and this is the KD tree that we're working with, the graph representation and the tree representation. So part B says, suppose you run the nearest algorithm on x is over here. What is the order that vertices are visited? Okay, so the first thing I did is I calculated all the distances between x and the various points that already exist in the KD tree and just listed them over here. All of these are calculated using the distance formula, so if you want to confirm them, you can go ahead and do that. But I did this ahead of time because that's not really what the problem's about. Okay, so in order to do this, we have to keep track of our current best point. So we can have our current best down here, and we have to keep track of what point is our current best and also what is their distance from x. So when we initially start, we have no point, and so we can just keep that distance as infinity. And we initially start up here at the root. So A is going to be the first point that we check. So distance from A to X is 3.162. 3.162 is smaller than infinity, so you can go ahead and replace that. So we can have A and then 3.162. And so we do actually visit A, so we can put that in there, and A we can consider visited. Now we need to see which side of A should we go to first. Should we go to this side first or this side first? Basically determining the good side versus the bad side. So we're going to look at the distances from C to X and then E to X. So from C to X, we have 5, and then from E to X, we have 3.162. 3.162 is less than 5, and so this becomes our quote-unquote good side. So we can just write that in. This is good. And then this becomes our quote-unquote bad side. This is bad. Okay, so we are going to move into our good side. So we are going to move this way down to E. We are going to visit E and see the distance between E and X and see if we should update our current best. So distance between E and X is 3.162, which is the exact same as the current distance that we have. In this particular case, we don't actually have to worry about tie breaking because visually looking at our graph, we do see that there is a point that's closer to X than both E and A. However, if you did have a situation where you had to tie break, whatever problem you're doing would specify a tie breaking method. In this particular case, we don't have to worry about it. We can just leave A as our current best because we know that eventually we're going to find something that's even better than both E and A. Okay, so now that we have visited E only has one child, so we don't need to worry about deciding the good side or the bad side. We can just visit its one child. And so we're going to go down to F, visit F. We see the distance between F and X is 1.414, which is less than our current best. And so we can go ahead and replace these with F and 1.414. And then F has one child, G. So again, we don't have a good side and a bad side. We're just going to visit G. So we can move down here, consider G visited. We look at the distance between G and X. It's 2.236, which is greater than our current best. So we don't update our current best. And I forgot to update this list, but after E, we visited F, and after F, we visited G. Okay, so now that we did that, we now need to see, is it worth it to visit our quote unquote bad side? So here is our bad side. And so how we decide whether we should even visit our bad side is we need to think on our bad side, what is the best point that we could have? So the best point that we could have would be this point right here, which is right across from X, because out of all the points on this side, that is the closest to X. So if we calculate that distance, that has a distance of 1. 1 is smaller than our current best, which means that we do have to go down our bad side. So we're going to go down our bad side. The first thing that we're going to visit is C. So we visit C. We check the distance between C and X. It's 5. 5 is greater than our current best, so we don't update anything. And now C has 2 children, so we need to determine the good and bad side again, except this time for the 2 sides of C. So we check the 2 distances from x. So we check b to x, and then we check d to x. So b to x is 2, and then d to x is 5.8. Since the distance from b to x is less than the distance from d to x, this now becomes our current good side, or the good side of C. This is our good side. And then this is our bad side, only of C. So the first place we're going to visit is our good side. So we're going to go to B. B is going to be visited. We can add that to our list. We check the distance from B to X, compare it to our current best. 2 is greater than our current best, so we don't need to update that at all. But now we need to see, should we go and visit our bad side? So how do we determine that? We check what is the closest point on our bad side to X. So this is the bad side of C that we are referring to. So closest point here would be this point right here, which is the point 4, 5, which you can tell because it's on the same x coordinate as C. So y coordinate as C, which is 5, and the same x coordinate as A, which is 4. So if we calculate this distance right here between 4, 5 and x, we get that this distance is 4.123. So I can write that in. This is 4.123, which is a lot greater than our current best distance. So we don't even need to go explore the bad side, and we can actually prune this. And so our final visited list looks like this. It's A, E, F, G, C, B.